Hello, everybody. Today what we'll be doing is we'll be taking up the Mobius assignment. Okay, let f equal g of h, where g and h are differentiable in R. Suppose that we have all these values, determine f prime at 4. So to do that, what we're going to do is we're going to write down f as a function of g and h. So we're going to get f is equal to g of h x, right? So then to find f prime, what we're going to do is we're going to need to do f prime equals to g prime of h of x. And then what we must not forget to do is we need a chain rule. So we have g of h. So times h prime at x. And now all we need to do is we need to plug in values. So you know it's f at 4, so x equals 4. So then we're going to get g prime at h of 4. So h of 4 is negative 6 right over here. So it's going to be g prime at negative 6, then h prime at 4, and h prime, when I say prime, that just means the derivative of. So h times h prime at 4 is 3, so times 3. And then y prime at negative 6, all right, this is a g. G prime at negative 6 is negative 2, so we're going to get negative 2. Negative 2 times 3 is 6, is negative 6. So over here, what we're going to do is we're going to say negative 6. Okay, given that f of x is continuous at x equals a, which of the following are true? So by definition, if something is continuous, that means that it has the limit x of a as f of x approaches, limit as x approaches a of f of x equals to f of a, because that means that as you're approaching the two sides, they're equal, and at that location, it also equals f of a. So this one would be true. Limit from x of a to f of x may not exist. No, this has to exist all around, so this is not true. Y equals f of a cannot be a horizontal asymptote. That's not true because what can happen is that, so if we get something like this, then this is f of a, this is f of a, y equals f of a. So, so what could happen? So that f of x is continuous. So what that's basically saying is that some may think that this is impossible because if y equals f of a is a horizontal asymptote, that means you're never actually touching it, because that means that as you approach infinity, you reach y equals f of a. But that's not necessarily true because there are functions where you pass the horizontal asymptote. So you could have a function that looks like this, and then just as it gets closer, it approaches that infinity. So in this case, you can't have that asymptote, and the function will still be continuous because it will it will still cross f of a. And so the limit of x of a would still exist there. And then finally, we have limit x approaches a minus f of x equals to limit of a. And this is true just because to have a limit as x approaches a of f of x equals f of a, this has to be true. So in this case, we would have two responses. It would be this one and this one. Clear it out. Now, I know that there are a lot of others, so if you have particular questions for exact ones, what you can do is you can post them in the comments, and then I will check and I will respond to those exact scenarios as well. Okay, which of the following statements are true? So over here we have if limit as x approaches a, f of x minus f of a over x minus a. So what this is the derivative. So we're basically saying if we take the derivative of f of x, it's going to give us some derivative. Then limit as x approaches a, f of x is equal to L. Now this isn't true, or isn't necessarily true, because this just tells us that as f of x, so this is basically saying that the limit at a will be the exact same as the derivative of it at a. And that's not necessarily true. We can have functions where we get one limit as we're approaching that point, but a different derivative for that point. A very easy example actually would be if we take, for instance, a line. So let's say our line is 2x plus 5. So then, as x approaches 1, our limit as x approaches 1 is going to be equal to 7. So limit as x approaches 1, it equals to 7. But the derivative, if we take the derivative of 2x plus 5, that is going to be equal to, so the derivative is equal to 2. So there you go. They're different, but both exist. So that's why this isn't true. Okay, if limit of f of x, then, so if the derivative exists, then limit as x approaches a from the negative side of f of x equals to limit of x as you approach from the right side of f of x. And this is true because what this is saying, this means that the limit exists. And we know that if you can take a derivative somewhere, then the limit there must exist. So this is true. If f of a exists and limit x of it, f of x exists, then f is differentiable at x equals a. This is not true because what this top part says, this basically states that it's continuous, even though it's not necessarily even stating that, because as we know, we can have a function like this. So here's a hole, and then here we have it filled in, and then we continue, where f of a exists, and limit of f and limit as x approaches a of f of x also exists, but the function isn't continuous. But even if you would have this hole filled in, just because a function is continuous doesn't guarantee that it's differentiable. And that's why this is wrong. If f is continuous at x equals a, then f is differentiable at x equals a. And this is false. And again, in some of the examples would be if you have a corner. So if you have something like this, then at this point, your function isn't differentiable because you would get two different slopes depending on where you're coming. Another function where it wouldn't be differentiable is if you have a horizontal and a vertical tangent. So over here you would get a vertical tangent, which means the tangent would be infinity, and that also doesn't work. So that's why this one doesn't work. So in this case, the only one which would work would be this one. Okay, which of the following functions are continuous on R? So for functions to be continuous, what that means is that it just means that they kind of never stop, right? That you can that they never stop. That's the best way. A really good way to think about it is that if you put the pencil and you try to trace the function, you never have to lift your pencil up. And so I'll just do some of the easy ones first. So over here, what we see is that we have a hole, and that hole is trying to be filled in. But what we need to do is we need to check if that hole is in fact correct. So if we factor the top, we would get we would get x plus 3 times x plus 4, x plus 3 times x plus 4 over x plus 4. So we see we have a hole, we can cancel that out. And then what we need to do is we need to check that the hole we're filling in over here makes sense. So that if we plug in x equals -4, we get -4 plus 3 equals to -1. So in fact, this hole is being filled. Therefore, this one would be correct. Then what we're going to do is we're going to look at sine x over 2 plus cos x. Now, what we always need to check is to see if a function is continuous, especially if it's a rational function, is we can check the bottom and see if it's 0. If this equals to 0, so there are what I was trying to say is that there are two options for rational functions not to be continuous. And that's both when you're looking at the bottom. And if the bottom is equal to 0, then you're going to get an asymptote of the function will be continuous. Or if the bottom is a hole, so if you can simplify the top and the bottom, then that will give you a hole and the function also will be continuous. So in this case, what we're going to do, actually, I don't like what we're going to do is we're going to check. So we know that there's no holes because you can't simplify anything. But now we just need to check whether the bottom can equal to 0. But I can tell you that the bottom can't equal to 0. And the reason for that is because cos of x is either going to be, has the range of -1 and +1. So it's -1 to +1 inclusive. And so no matter what you input for cos of x, this will always be bigger than 0. On the other hand, if we had a function such as sine x over 1 plus cosine of x, this would not be continuous because you could put in -1 and then you would get 0 on the bottom. So this function is continuous. Okay, then we're going to get into these tough ones. So now what root of x, so the regular just root of x, looks something like this. Now, all that root of x does is it allows for you to have the other side as well, because then at negative x, it's still positive. And as you're approaching zero, they will both equal to zero, so this function is in fact continuous. And we'll check that on Desmos later, just in case if you don't believe me. Okay, so now we have our function ln of x. Now, ln of x, what happens is that any logarithmic function, um, what happens is that logarithmic functions look like this, where they never reach zero, but as your x approaches zero, as your x approaches zero, your y approaches infinity. That's because you can never get to zero, but you can try to get there. And that makes sense as well if you're thinking of logarithm as the inverse of an exponential function right here. You see that it's reflected. Now, basically, what's going to happen is that if we say we can have negative terms, right, because you can't take a logarithm of a negative number. So all that will change is if we have absolute value, will become available to us as this, but still, you will never be able to reach zero. And that's why this function would not be continuous. Now, let's quickly check me on Desmos, and you would be able to actually see those graphs. So let's go to Desmos. So let's clear all this. So the two functions we want to check was square root of x, and actually we want absolute value of x. Oh, and I actually drew it incorrectly. I apologize. Yeah, because the y. So what I did is I drew it. The mistake I made during while I was trying to say is that you would have this one going over here, and that's wrong because you can't have a negative. The square root will never give you a negative, but it will look like this. Okay, and so this is in fact continuous. And right now we're not talking about differentiability, so I'm not really going to bring it up, but be careful. Not everything that is continuous is differentiable. So over here, I think that it's actually just going to be, it might be a vertical slope, but I would need to check. But as we see, it is continuous. It is, I can drop my pencil and trace it without any problem. The next function that we were looking at, which I said is not continuous, was ln of absolute value of x. That's the problem. So we just need to use parentheses there. I'm not sure why that's. Hopefully this works now. And again, I made a mistake. I apologize when I was drawing the function. But what I want to show you again is that you will never reach zero. So the reason that it goes down like this in absolute value is because so before you couldn't access the negative. So if you do access the negative, it should be the same as the positive, just on the other side, which makes sense. Now, what's going to happen is that we're going to approach zero but never reach it on either side. Again, because you can't get, like, nothing to the power of anything will ever give you zero. You'll be very close, but it'll never give you zero. Yeah, and that's that. Yeah, so let's go back. And so now we know that we're going to pick this, and this one. Let's click next. Okay, which of the following are correct uses of the chain rule? So this isn't it. So the correct usage of the chain rule is that dy over dx. You could say that that is equal to dy over dv times dv over dx. And again, you can think of it as fractions here, that you're just simplifying this and getting this. So if the fraction matches up, it works. So here you can see you can cancel these out. So this one would work. Over here, we're trying to get dy over dx. So here it wouldn't work because it would be dx over dy. And here we're trying to get db over dt, but here we have b and x. So that won't work either. So it's just that one. Okay, which of the functions are differentiable at x equals 0? So now we have to do is we have to be very careful because even if a function is continuous, it isn't necessarily differentiable. So we just need to check that. So first, sine of x over x, that is not, it doesn't exist at 0. So therefore, this isn't differentiable. Over here, so for a function to be differentiable at a point, there has to be two conditions that are met. Firstly, that the limit exists there, and the second is that the derivative from, so right now, I'm sorry, I'm talking about the piecewise function. And basically for a piecewise function to be able to have a derivative of something, you would need the left side and the right side to equal. So that basically means that the limit from both sides exists, and the derivative at both is the same, has the same value. So what we need to do is first we need to evaluate. So in both cases, if you plug in 0, so 0 times 0 plus 4 is 0, and root of 0 is 0. And then what we need to do is we need to take derivative of both. So here we have x squared plus 4x. If we take the derivative of that, we would get 2x plus 4. And now the derivative of 2x plus 4 is 0. I mean, sorry, what am I saying? The derivative of x squared plus 4x is 2x plus 4. And then if we evaluate it at 0, you would get 4. On the other hand, if you take the derivative of x, the derivative of x is equal to 1 over 2 root x. And the way you get that is because root of x is x to the power of a half. So you would drop the half, and then you get negative 1/2. So that's how we get equals to 1 over 2 times x to the power of negative a half. And that is just equal to 1 over 2 root x. And if you evaluate it at 0, you clearly see that you don't get 4. So therefore, this also doesn't work. Now, sine of x is a very tricky case. So what I'm going to do is I'm going to quickly draw you absolute value of sine of x. So if this is equal to sine of x, so it's going to go something like this. And the same thing over here. So now, for it to become absolute value, what's going to happen is that the negatives are going to become positive. So it's going to go like this, and like this, and like this. And so this would disappear, this would disappear. What's important to see is that actually, when we get to 0, what's going to happen is that we're actually going to get two different slope lines. Because as we see, as we approach 0, if we take it from the left side, our slope is going to look something like this. But from the right side, it's going to look something like this. And now I just realized orange on red doesn't look so good. So let's try purple. Yeah, so like this and like this. And because of that, you're going to get two different derivatives, or tangents to be more exact. And so that's impossible. That is a big no-no. So this one doesn't work. But I just want to quickly bring up that cosine of x actually would work. And again, to do that, I'm just going to draw it. So for cosine of x, what happens is that this is our function, and then this is our function. And so if we take it at absolute value of it, this would disappear, then it would become like this would disappear, this would disappear. But what we notice is that as you're approaching 1, the slope is going to be the same no matter where you, like the slope here is going to be the same. There's just going to be a horizontal slope. So absolute value of cosine of x, so cosine of absolute value of x, that derivative would exist at 0. So you could derive that at x equals 0. Finally, we're going to get x, absolute value of x plus 1 over x. And so what we want to do is let's quickly define it. So x, absolute value of x plus 1 over x. So if we define that, it's going to be x times x plus 1 over x at x plus 1 over x being greater than 0 or equal to 0, and x times negative x plus 1 over x for x plus 1 over x smaller than 0. So then if we solve for this, then it's going to be x squared plus 1 is greater or equal to 0. And so that is, I believe that's always the case actually, unless I'm mistaken. So, no, I clearly did something wrong. You give me a sec. Because if you have a -2, for instance, yeah, -2 would give you something here. So what we need to do is we need to factor out, if we factor out x, we get x times 1 plus 1 over x squared is greater or equal to 0. So one of our solutions is 0, and the other one, So instead, what I'm going to do, so this is getting a bit confusing. So what I'm going to do here is if we say that x equals 0, I think we're actually going to get an asymptote because we're going to get something that's undefined. So we need to work to find a limit. And this is going to be equal to 0, and this is going to be equal to infinity. So it's going to be 0 times infinity, which is undefined. So I believe this one would not be differentiable, but I'm going to check on Desmos and retroactively try to explain it. So it's going to be x times absolute value of x plus 1 over x. And let me try to clear all my messy works. And as we see, it isn't defined at 0, just as we kind of saw from a first glance. See, there's going to be a big hole here, the jump. So we kind of predicted that. And so what we see is that here, none of them are differentiable. Okay, so here it says let f be a continuous function that takes on these values. And so a really good way to visualize this is firstly to remember the mean value theorem, which basically, well, I'll show it to you. So here we have -2, -4, so it's going to be somewhere over here. Then it's going to be f at -1 is -9, so f at -1 is -9. F at 0 is 9. F at 1 is -4. 1 is -4. And then f at 2 is 5. And so basically what we kind of think is that it's basically asking us when do we know for sure that the function is going to cross 0? That there's going to be a f of x equals 0. So from -2 to -1, and we can look at the multiple choice here. So from -2 to -1, we don't know. So the function could potentially go like this, but we don't know. All we know for sure is that between this function and this function, all of these values will be addressed. So all the values between -4 and -9 will be addressed. Then, and we know that because we can kind of see it, that if we have to go from this point to this point, this distance will have to be traveled. Then from 1 to 2, we know again that from this point to this point, all of this distance will be traveled. And to travel all that distance at some point, we're going to need to cross x. So therefore, this one would work. Then from 0 to 1, again, we know that all of this distance has to be traveled. So we know that at some point, this value will be crossed. F of x is equal to 0. So this also works. The -2 to 0 also works. Because here we know that we have to go from here to here. And so we know that this distance will be traveled. And again, that means we know we're crossing 0. So this one would also work. So we go 1, 2, 3, click next. So let f of x equal x squared, g of x equals sine of x, and h of x. Okay, so here what you need to do is you just need to be very careful and apply all your chain rules. So let's go through it. So f at g of h. So f at g of h, and this is of x as well. So h is 1 over x. G is, so it's going to be, so f at g of h. So h is 1 over x. G of h is going to be sine of 1 over x. And then f. So the way you do this is that you just see where your x is and you plug in what's there. It's composite functions. And then finally, we're going to do x squared. So it's going to be sine of 1 over x and all of this squared. So now if we take the derivative, we just need to be careful with applying our chain rule. I'm just going to check that I did everything correctly. So it's h, g, and g of h. Perfect. So then we're going to take, so the first thing is going to be 2 sine of 1 over x. Then we need to change it to sine over 1 over x. So it's times cos of 1 over x. Then we need to change it to 1 over x, which is going to equal to times -2, or to be more precise, it's going to be negative, if we bring out -1, times 1 over x squared, because it's going to be, so if we think about it, x times to the power -1, so we bring -1, it's x to the power negative, like this, to represent again. So here we actually get it, so sine x, -1 cos x, -1 x squared, so this one works. So g of h of x, so g of h, so that's going to be sine of 1 over x. So if we derive that, we're going to get cos 1 over x times negative 1 over x squared. And here we actually do see that as well. Negative cos x to the power of negative 1 over x squared. So f of g, so it's going to be sine of x squared. So we're going to get 2 sine x, and then we change it to sine x, so that's going to be cosine x. So this one also works, and then we have h of f of g. So h of f g. So if we put g into f, we're going to get sine x squared. So h of sine x squared. And then if we take h of that, it's going to be 1 over sine of x squared. So another way, you can just look at this to make it simpler for yourself. It's going to be sine of x to the power of negative 2. And then what we can do is we can start deriving it. So what we get we get negative 2 sine x to the power of negative 3 times cosine x, because we need to change it to this one over here. And we see that this does not equal to this, because here sine is something's real here basically. So this does not work. So let's pick all the ones we don't work. So 1, 2, 3. I'm gonna click next. Okay, and this question I take up on a separate video, which I will post as well, because it's a very long-winded explanation, and I'm not ready to do it here. So you will see a different video about it. Hopefully this helped everybody, and I hope everybody has a great day. Have a great reading week as well. Make sure to relax, and yeah, you'll see some more videos coming from me, hopefully, for reading.